So welcome to exercise 9. As always, we will start by looking at what this exercise is about before we start calculating stuff. So in exercise 9, we're asked to consider a homogeneous Poisson process that we call N. And this homogeneous Poisson process has an intensity rate lambda, and we call its arrival times Ti. Now, in the past few days, I guess you guys have been learning about how we may look at the claims number process. So one way we can think the claims number process is just in the way of the good old homogeneous Poisson process, where we say, well, take a time t. Then the number of claims that have occurred up until time t is Poisson distributed with some mean value parameter. Now, if it was an inhomogeneous Poisson process, I would have written mu of t. Now, since we have a homogeneous Poisson process, the expected number of claims at time t is just lambda multiplied by t, right? So this is one way we may look at the Poisson process, is in terms of how is the number of claims distributed at any time point. And also, if you look at the definition more carefully, you will remember the four criteria that the Poisson process has to have independent increments, the increments are Poisson distributed, and so on and so on. Now, in the second week, I guess, or maybe already in the first week, I'm not sure, you guys also learned another way to look at the Poisson process, which was the renewal representation of a homogeneous Poisson process. So you can look at it either in terms of the traditional definition, or we may think about it as a renewal process. Now, what do I mean by renewal process? Well, what I mean is, instead of looking at how the number of claims is distributed, I will look at how the inter-arrival times are distributed. And the inter-arrival times in a renewal representation, we call these inter-arrival times Wi, and Wi is the amount of time that passes from the I minus first claim to the ith claim. So we look at the inter-arrival times Wi. How are they distributed? Well, a Poisson process that is homogeneous has inter-arrival times Wi, which are exponentially distributed. And in our case, since it has intensity lambda, the inter-arrival times are exponentially distributed with parameter lambda. Yes? This is the renewal representation, where we look at the Poisson process not in terms of how its claim number in some time interval is distributed, instead how the amount of time that passes between two claims is distributed. So in exercise 9, what we will do essentially is we will try to show that whether we look at a Poisson process by looking at the claim number distribution or by looking at the inter-arrival times distribution, it doesn't really matter, because the two things, they just represent two sides of the same coin. So in part A of exercise 9, we will be considering the distribution of the arrival times. So just to make it completely clear, the Wi, they are what we call the inter-arrival times. And then the arrival times, Ti, they are given as W1 plus W2 and so on up until Wi. And the Ti are what we call the arrival times. Yes? So if I had to draw some kind of drawing where we, for example, have a Poisson process sample path like this, and like the first jump occurs at time t1, and then the next at time t2, and then the next at time t3, for example, then this is what is t1, this is t2, this is t3. However, the length of this interval is what we call w1, the length of this interval is what we call w2, and the length of this interval is what we call w3. So the w's are the inter-arrival times, so how long time passes between arrivals, whereas the t's are the arrival times, which means exactly when the claims arrive. So this isn't exactly rocket science, but it's still nice to just be completely sure of the notation. So in A, they tell us, well, look at the renewal version of a homogeneous Poisson process. So look at a homogeneous Poisson process defined in terms of its inter-arrival times. So here the Poisson process will be in at time t will be given as the number of claims that satisfy that the time of their arrival is before the time that we're standing at. Yes? Where the time of each claim's arrival is or can be defined using the inter-arrival times, W, as we have been talking about down here. Yeah? Okay, so what they want us to do, first and foremost, is to consider the distribution of the arrival times. So they say for two time points t1 and t2, calculate the distribution of the first two arrival times. Find the probability that t1 is smaller than or equal to little t1, and that the arrival time of the second claim is smaller than or equal to little t2. And that is what we will be doing in A. Of course, they also ask us to find the probability that t1 is smaller than or equal to t. But that isn't really interesting for us right now, but let's just write that up as well then here. But in this video solution, I will only solve the second part, because you guys can do the first part on your own. Okay, so that's what we'll be doing in A. We will find this probability here. What we'll be doing in B is we will consider the first definition of the Poisson process. So the definition of the four criteria. It has to start almost surely in 0. It has to have independent increments. It has to have Poisson distributed increments. It has to have what do we call it? Cadillac sample path. So consider the four criteria definition of the Poisson process N of N, and find. And then they ask us to find the probability that N of t1 is greater than or equal to 1, and N of t2 is greater than or equal to 2 at the time points t1 and t2 that we also considered in A. And of course, what we're going to be doing here is actually to show that these two things are equal to each other. So we will calculate both of them and conclude, well, apparently they have the same probability. And if we use our brains a little bit, we will also be able to conclude that, well, the event that the first arrival arrives before t1 and the second arrival arrives before t2, well, that event is exactly the same as the event where at time t1 we have already had more than one arrival, and at time t2 we have already had more than 2 arrivals. Yes? So basically, exercise 9 is just for us to really understand and grasp that the renewal representation of a homogeneous Poisson process defines exactly the same thing as the original definition of a homogeneous Poisson process. And this was just an introduction to the exercise. It's okay if you didn't watch this one. I mean, I'm just talking here. So in the next video, we will be calculating A, and in the video after that, we will be calculating B. So see you guys.